Here we have part 5, graphing rational functions. So here's a little bit more complex function. It states that 3x squared minus 12x minus 15 all over x cubed minus 2x squared minus 25x plus 50. So again, the first step would be to factor out the numerator and the denominator. So let's see. So obviously we see that there's a 3 that's common in the numerator, right? So we can write this as f of x is equal to 3 times x squared minus 4x minus 5. Right, and if we just look at this, it should be clear that negative 5 and 1 have a product of negative 5 and a sum of negative 4. Therefore, we can really write the numerator as 3 times x minus 5 and then times x plus 1. Now we look at the denominator, right? And the denominator is this, and really we can just do the grouping method, right? In one of the previous lessons I did talk about grouping, so you can group these two. So let's just see what that is. So grouping this, we know that x squared is common. X squared times x gives us x cubed minus 2. We have minus 25 times x minus 2. Really, this is x squared minus 25 times x minus 2, and again, because this x squared minus 25 is in the form of a squared minus b squared, we can really write this as x minus 5 times x plus 5, and obviously this is just x minus 2. So now we have this, right? And really on the top we have this. So this one we can just write this as x plus 5 times x minus 5 times x minus 2. So this is what we have here, really simplifying. I'll just erase everything else to make it look more simpler. So this is what we have as the factored form here. So it's always important to factor out the function again, so that we can see what the common factors are to determine which could be our wholes, and then what are the vertical asymptotes. Obviously for horizontal you don't really need to factor it out. So this is what we have as our factored form. We have 3 times x minus 5 times x plus 1 all divided by x plus 5 times x minus 5 times x minus 2. So looking at this, right, we can obviously determine our vertical asymptotes and our wholes. So we know that x minus 5 is in common again, so we can eliminate this because this is a common factor, and so set one of these factors to 0 and we get x is equal to 5. Therefore the x coordinate of the whole must be 5. And now we're just substituting 5 back into the equation, really. So 5, we can add that to 1, right? So 6 times 3 is 18. And then we would do 5 plus 5, 10 times 3, that's 30. And really 18 over 30 is 3/5. Therefore our whole is 5, 3/5. So our whole would be at the point 5, 3/5. Right? Again, that's where the removable discontinuity is. And then we really can't eliminate any other factor. There are no more common factors. Therefore, the x plus 5 and the x minus 2 in the denominator really are the vertical asymptotes, or they represent the vertical asymptotes. So we really set each of these factors to 0 to determine the equation of the vertical asymptote, again because these two factors are distinct in the denominator. And so the vertical asymptotes here would be x is equal to negative 5 and x is equal to 2. So these are our vertical asymptotes. And now we can obviously look at our x-intercept and our y-intercept. And the x-intercept is the value of x when y is set to 0. So really, again, the numerator needs to be 0. But again, 5, 5, we cannot say that's an x-intercept. Again, as I've mentioned in my previous videos, really, 5, 3/5. The whole is at x coordinate 5. Therefore, your x-intercept cannot be 5. Again, because whole is the most dominating factor to consider. So x-intercept, we're only looking at negative 1, 0. So that's our x-intercept. Now comes the y-intercept. Again, the value of y when x is set to 0. And so you can just substitute that whether you want to do it here or here, and you get 0, 0, comma, -3/10. So that's the value you get. And now your domain, right? Your domain is really the set of all real numbers such that x is not equal to -5, 2, or 5. And so that's really our domain. And why I say this is again because our vertical asymptotes were -5 and 2, and there's a hole at 5, 3/5. Therefore, again, these all three numbers, all your holes and your vertical asymptotes must be excluded from the domain, because at these values your function is undefined. So these are the values we have now. And now we can look at the horizontal asymptote. Again, you can either have the slant or the horizontal. So clearly here the degree in the numerator is 1 less, or it's less than the degree in the denominator. Therefore we know by the rule that there must be a horizontal asymptote at y is equal to 0. And therefore the slant asymptote becomes non-applicable here. And then we have the last thing left, which is to see if it crosses or not. Again, and really when we look at this, we know that the horizontal asymptote is y is equal to 0. And so if we think about this, we can set f of x, we can set that to 0, and really move this denominator to that side. And really what that gives us, that gives us a product of 0 here. So think about this, y is equal to 0. We have this in the denominator, and this shifts to this side, giving us 0 altogether. And so really we say that 0 is equal to 3x squared minus 12x minus 15. And clearly we see that a 3 is you can just factor a 3 out, right? As we have done previously here, really just gives us x minus 5 times x plus 1. So if we just take the 3 out and really do 0 divided by 3, that's just 0. So we're really left with x minus 5 and x plus 1. Again, there was a 3 here, but we took the 3 here. 0 divided by 3 is just 0. And now we look at this, we see that there's obviously x minus 5. So we may be like, oh, it may be crossing at points 5, 0, and -1, 0. However, we have to be careful before making this assumption, because again, there's a hole at 5, 3/5. Again, the hole is the most dominating factor of all. So really, we cannot say it's crossing at 5, 0, because that's where the hole exists. So we won't consider this. However, we do consider that it crosses the point -1, 0. And again, it's obviously the y coordinate is 0 because it's crossing that horizontal asymptote, that equation y is equal to 0, which is obviously the x-axis. So we have all the key information now, and we can graph our function. So let me just graph it now. So now we can just graph this function. So let me draw the x and the y-axis here, right? So this is obviously the x-axis, and this is the y-axis. Again, it's just a sketch here that we're looking at. So here we again know our asymptotes. There's a horizontal asymptote y is equal to 0 again, which is just the x-axis. So let's just say this dotted line here is the horizontal asymptote. And now looking at the vertical asymptotes, we have one at -5, right? So this is -5, and then we have another one at x is equal to 2, right? So we make another one here. This is x is equal to 2, and at -5, right? And we have one which is x-axis, really y is equal to 0, the horizontal asymptote. And we look at our x-intercepts and the y-intercepts. So we have one at -1, -1, 0 as our x-intercept, right? So this is the point that we're looking at, really. And then besides this, we obviously have our y-intercept, right? Our y-intercept is 0, -3/10 or -0.3, and that's gonna be somewhere here, really. So that's weird. And now you can plug in further values such as -4, and you will see points here. Something like that is where you're going to see. And then you can plug in more points here, and you'll see it just continues to go like this. Again, approaching these asymptotes, but not really touching those asymptotes. So it's just going to approach, it's going to tend towards those asymptotes, but not actually touch them. So this is one portion of your graph, really. Plug in other values here, like -6, -7, you see another curve that's going to be something like that. And similarly, you plug in values greater than 2, you will see something like this. But again, it's important to understand that there was a hole at 5, 3/5. So we say that that's something like this, I guess, because it's just a sketch. So that's where our hole is, right? It may be a little bit messy, but this is where our hole is, right? At 5, 3/5. And so that's the hole. These are asymptotes. This is our horizontal asymptote. This is one portion of the graph, the other portion of the graph, and this is the central portion of our graph. So we have labeled the hole, the asymptotes, and really everything else, except it's the point where it crosses. It's important to understand. And so it says it crosses at the point -1, 0, and this is highly interesting because if you think about this, it makes sense, because you know -1, 0 is your x-intercept, and it's an x-intercept that makes sense, that we got by factoring. And really we know our horizontal asymptote is y is equal to 0, which is the x-axis itself. Therefore it makes sense to say that -1, 0 is where the x-intercept is, and also it's the point where the graph is crossing the horizontal asymptote. So really, when we say it's where it's crossing, you can draw a circle, although you always want to be careful. You call this the hole, and you can label this as the cross. And like with the hole, right, you just continue to go in that one particular direction. You just continue to draw this. It's important that with the cross, you start like this. You're going, and then you retain that direction. You make sure that your direction continues. So it's something like this, and then it continues to be approaching this vertical asymptote here at x is equal to 2. So this is your graph here. It has crossing, has asymptotes, holes, and everything. So thanks for watching, and there will be one more lesson on rational functions that involves graphing. So thanks for watching.